Today we are going to talk about how we can model polynomial functions using something called finite differences. So our learning goals for today, we need to be able to use finite differences to determine the degree of a polynomial that'll fit our data set. And then we also are going to focus specifically on cubic functions and being able to write the equation when we are given either a graph or points of that function. So our lesson today is based upon what we see here first, and that is if a polynomial has degree n, so n is standing for a number, then the nth order differences of equally spaced x values are non-zero, so meaning not zero, and constant. Constant means that they're going to be the same. So, because we're working with n, an example would be if the degree of a polynomial is 5, then the fifth order differences would be constant, meaning they would all be the same number. Now, it's important that we know what nth order differences are, because if you don't know what the fifth order differences are, it's kind of hard to use those to help you. We find differences, we kind of use a Pascal's triangle-like approach, only we subtract instead of adding what's above. So let's just say if you had, these numbers in a first row, the next row you'd take the two above to get the next one. So that's what I mean when I say Pascal's triangle-like approach. You would just be taking the difference between these two. So -4, -2, and we always write it as positive. So this difference would be 6, this difference here would be 12, and then on the next row you would do these two together. So that idea is how we find our finite differences. Now, the key is that the x values have to be equally spaced. You can't just put in any numbers that you want and find their differences and expect for that to tell you what degree the answer is going to be. So here, when we're looking at a table, we can tell that these are equally spaced because my x values are 1, 2, 3, 4, 5, 6. So that means that these f of x are my starting point. So these are my f of x values that are equally spaced. So that means that the first order differences are what I get when I find all of these differences here. So the difference between 5 and 5 is 0. There is no difference between them, they're the same. The difference between 5 and 7 is 2 units. Between 7 and 11 would be 4. Between 11 and 17 is 6. And between 17 and 25, that difference is 8. So these are the first order differences. So we continue the pattern. These are going to be the second order differences. So 2, 2, 2, 2. So my second order differences, they're non-zero, and they're constant. They're all the same. So that means, since it's the second order differences, that this one, the polynomial that will fit that data, is degree 2 because of the second order differences. Not because this number is 2, because it's the second order. All right, so let's look at that one more time. So again, equally spaced 1 through 6. The difference between -2 and -6 is 4 units. -6 and -6, that's 0. Between -6 and 4, that's 10 units. Between 4 and 30, 26. And between 30 and 78, that would be a difference of 48. So here's my first order. So second order, here's 4, 10, 16, and 22. So here's my second order differences. So this is definitely not a quadratic that models this data. Third order differences here, 6, 6, 6. So the third order differences are non-zero and constant. So that means the type of polynomial we would be looking for to model that data would be of degree 3. So that helps us meet our first learning goal there. We can use those finite differences. We know what type of an equation should model that data. And that's important because it's hard to figure that out if you can't visualize it. If you can look at a picture, most people can say, oh, that looks quadratic, that looks cubic, that looks linear. So here's a way that we can do that without having to plot all of those points in the coordinate plane. All right, so our second learning goal, we want to be able to focus on the cubic function, so degree 3, and writing the equation. This is all based upon something that we learned back in Unit 3, and that was if k is a 0 of a polynomial, then x minus k is a factor. The reason why this is important is because anytime they're giving you a graph or giving you some points and they want you to write the cubic function, the ones that they're going to give you are going to be zeros. At least 3 of them should be. So that means zeros, remember, are x-intercepts. So when they give you x-intercepts, they're really giving you a factor. You know that cubics have to have degree 3. So if you have 3 factors, plus 1 additional point, you have enough information to write the equation. So I'm going to show you what I mean here. We need 3 factors. So we have -2, 0. So that means -2 is a 0, which means that x minus -2 is a factor. Then we've got 1, 0 here. So that means if 1 is a 0, x minus 1 is a factor. 3, 0. If 3 is a 0, then x minus 3 is a factor. Now, this is what we did in Unit 3. They said write a polynomial of least degree and leading coefficient 1. And so this is all we had to do because we knew, according to the directions, that the leading coefficient was 1. Here, the leading coefficient is no longer necessarily 1. We have to find it. We need to know what A is. So that's why we need this 1 additional point. The 1 additional point helps us to find A. Just like we did with quadratics, you can't find the A value unless A is the only variable. So we need, these ones were all factors. These gave me all my factors. This one is my extra point. It's not an x-intercept, it's not a 0, it's a y-intercept. So that is my extra point that I'm going to plug in for x and y. Because when I do that, that means the only variable left will be my a. So I'm going to plug that in. So 2 is the y value, equals a is what I don't know and what I'm trying to find. X is 0. So I've got 0 plus 2 times 0 minus 1 times 0 minus 3. So I've got 2 equals, I've still got the a, That's going to be 2 times -1 times -3. So when I simplify that, 2 times -1 is -2, -2 times -3 is 6. So I've got 6a. So to get a alone, I'm going to divide by 6. A is 1/3. So that means now I can write my equation again because I've got the a to put in. So y equals 1/3 times x plus 2 times x minus 1 times x minus 3. And that is my equation. Now, it's important that you pay attention. This one did not say what form we needed to write it in, so we can leave it just like that. But do be careful. If for some reason it would ask you to write something in standard form, then you would have to multiply all of that out. I don't think many of them are going to do that, but just so you know to pay attention to those directions as needed. All right. Next, also writing a cubic function, but this time it just says it passes through the given points. Well, if you notice, 3 of the points that I'm given are x-intercepts. So this is exactly the same as example 2, except that instead of the picture, they just gave you a list, because now this is my extra point. That's my x and my y. So now I'm going to do the exact same thing that I did in example 2. I'm going to write y equals a, and then x minus 0, x minus -3, and x minus 5. So plug in my x and my y. Into these points. So y is 3. X is -2. So I plug those all in. And now, -2 minus 0 is -2. I've got times -2 plus 3, which is 1, times -2 minus 5, which is -7. So, -2 times 1 is -2. -2 times -7 is positive 14. So I've got 3 equals 14a. So to solve for a, that means I need to divide both sides by my 14. So a equals 3/14. Does not reduce, so go ahead and plug it in. So y equals a 3/14. Now, x minus 0, we just write x. So I take away that minus 0 in my final answer, times x plus 3 times x minus 5. There is our equation. So that takes care of our second learning goal. We can write a cubic function when we're given its graph or points. And example 1 took care of the first. So that is it for today.